Okay, so fine. That's where we left off yesterday anyway. Okay, so option number one, and the less good way to solve this problem, although it does work, is to use conservation of energy. All right, so here's going to be the deal. What we're going to do is we're going to say this. I know that if I calculate the gravitational potential energy at my first point and the kinetic energy at my first point, that ought to equal my gravitational potential energy at point 2 plus the kinetic energy at point 2, right? Because the only force acting on it is gravity, and that's conservative force, so our total energy shouldn't change. Follow? All right, so here's what you end up getting. This is negative, well, here, shoot. What's the best way to write this out? I guess I'll write it out in table form like I did on this piece of paper. All right, so here we go. So U1 is negative G times M. What is that M there, you guys? Mass of the sun, right? Because that's what Halley's Comet is orbiting. Times little m, which is the mass of Halley's Comet, divided by R1, which we have up here, right? Does everybody agree that I can plug those numbers in and get an answer? Yeah. All right, so if you do that, here's what you get. You get negative 1.4988 times 10 to the 9th times whatever the mass of Halley's Comet is, joules. All right, and you'll see in a minute why I kept track of all those sig figs. Everybody good up to there? All right, now, the kinetic energy at point 1 is 1/2. What mass do I use? The little mass, right? Because it's Halley's Comet that's moving, times its velocity squared. And that velocity would be v1, the 54,600, right? So if you figure that out, you end up getting positive 1.4906 times 10 to the 9th meters. Follow? Which means that my total energy at point 1 is the sum of those two numbers. Thanks, Jake. And it gives you this, negative 8.212 times 10 to the 6th times m joules. All right, now you can see that because of these significant digits, this number is probably somewhat flawed, right? Which is why I think I couldn't get a satisfactory answer. Cool? All right, because like my eccentricity that I used was only 3 sig digs. And here I'm keeping track of 5 sig digs, right? So there's definitely some problems with my calculations. I think that's why I couldn't get it to work out. All right, but so does everybody understand what I did here? All right, now let's look at point 2. So at point 2, it turns out that the gravitational potential energy is, once again, negative G times M over R2, and you get this number, negative 2.5144 times 10 to the 7th meters. Not meters, sorry, M times joules. I can't say that right. This number times the mass of Halley's Comet, whatever that is, that many joules. I had a tough time spitting that out. Everybody cool up to there? All right, now, how do I use that information to find the kinetic energy? Yeah. This, plus whatever my kinetic energy at point 2 is, has got to add up to this number again, right? Times m joules, right? Solid? All right. So, what ends up happening, remember before I just had 54,000 joules? If you use that number, the only way this works is if this kinetic energy here is negative. You can't have negative kinetic energy. So, anyway, this ends up working. So this number turns out to be 1.9632 times 10 to the 7th meters. I did it again. Times m joules. Okay. Cool. Yeah. All right. So this mess then, this number, has got to equal 1/2 mv squared, right? Say it again. and then the m's cancel, and you can solve it, right? And so the velocity you get if you use this method is like 5,800 meters a second, which again is not accurate, but it's at least neighborhood. A little big neighborhood, right? Neighborhood. Cool? All right, so that works. Yay, conservation of energy. All right? Now, remember, what started all of this was this. What I told you guys was that Kepler discovered this law of areas, that in a given time, your planet is going to always sweep out the same area. For any fixed interval of time, it'll sweep out the same area, right? And what I commented on was the fact that this is the exact same thing as conservation of angular momentum. Cool? So remember, angular momentum is mass times r cross v. Right? So look at this drawing here. So when we're looking at our closest point, my velocity is this way, right? And my radius is this way. So what's true about that angle? 90 degrees. So I can just do, literally, radius times velocity. Right? So at this point, if I do mass times radius times velocity, and then I do the same thing over here, where I have the same relationship, right? I ought to get the same answer, right? So here is sort of the better way of doing this. Go, brain, Kepler. So Kepler's second law says that the initial angular momentum has got to equal the final angular momentum. Or maybe I should say this. The angular momentum at point 1 has got to equal the angular momentum at point 2. Right? So, mass of Halley's comet times the radius at point 1 cross the velocity at point 1 has got to equal the mass of Halley's comet times the radius at point 2 cross the velocity at point 2, right? So this equation gets simplified. Your masses cancel out because they're both Halley's comet. And both of these are just r times v, right? Because at those points, your angle's 90 degrees. So you get r1 v1 equals r2 v2. Oh yeah, that's Star Wars, right? Okay, so let's see, what do we got? So our r1 was this. So this is 8.856 times 10 to the 10th meters times v1, which was 54600 meters a second. That's got to equal r2, which was 5.279 times 10 to the 12th meters times v2, and solve it. So multiply and then divide by this thing, and you get v2 is 916 meters a second. And the posted value I saw was 920. So.
Great. So it's supposed to be the same as the other one we got, and then it kind of one.
Okay. So you can see there are some flaws with the other ones, and I really think that they stem from the significant digit issue.
Okay. Yeah, that's like a 4,000.
Yeah, I get it.
Have we figured out some figures for the AP test yet?
Say it again.
Figured out what the AP test wants.
It doesn't seem to be an issue. I haven't seen anywhere where they said that they take off points for that. Cool. The website that I checked, I think it's at 920 if I remember right. I'm going from memory, but it was real close to that. Cool, you guys? All right, and on one of the AP tests, I saw a problem like this that said, at its closest, this thing is moving at this velocity. How fast is it going at its farthest? And it's literally like a one-step up. Okay? So, conservation of angular momentum is a great way to deal with planetary and lunar motion. All right, cool. All right, cool. So that's the first two laws, along with the smattering of conservation of energy. And also notice the fact that the gravitational potential energy is negative doesn't change how you solve the problems. You still just do total energy equals total energy. All right? All right, finally, the third law. I'll be honest with you, I always forget this law because you don't really need it if you know Newton's laws. Okay? So, you can see this equation could be easy to forget, yes?
Yeah.
All right? I don't understand how you could forget it, right? Okay, so Kepler's third law, basically what he realized is that the square of the period is proportional to the cube of the radius. That's, I believe, how Kepler stated it. It was something along those lines. And then since then, people have figured out this gravitational constant, and we've been able to write it this way. All right, check it out. Here's where this all comes from. Look, if you've got an object in circular orbit, then the gravitational force is G times M. Let me write it the way that I've been writing it. G times M over R squared, right? And that's keeping the planet basically in circular orbit, right? Right, now the fact is it could be elliptical, and that throws things off a little bit. And the book kind of does this hand wavy thing and says it still works for ellipses. I'll come back to that in a minute. But so the idea is this has to be providing centripetal force to keep the planet going in a circle, right?
Yeah.
Oh, well, centripetal force is mv squared over r, right? Follow? All right, so let's see. I feel like I ought to be able to rearrange this and solve for v. So here's what I've got right now. Setting this equal to this, I get g times the mass of the body at the center of the orbit times m over r squared equals m times v squared over r. The first thing I notice is that the little m's cancel out. I can multiply both sides by r, and one of the r's cancel on both sides. Oh, well, that means that v squared is gm over r, right? All right, but we're trying to come up with something about, not about the velocity, but about the period, right? Well, look. Velocity is, if it's going in a circle, it's just the circumference over the period, right? Okay, well, so that means that this thing squared is equal to that, right? So now I've got this thing, gm over r equals this thing squared. So that's 4 times pi squared times r squared over t squared. And then solve for t squared and you get that other mess. So multiply by t squared, move your r's. If you solve this, you get exactly that expression that we just had over there. 4 pi squared r cubed all over gm. There you go, Kepler's third law. Did I do that right? Move that. Oh, r cubed, thank you. Make sense? So I almost never use Kepler's third law. I just remember, really, it's just a combination of this and the universal gravitation law. Cool? All right. Questions about that? All right. Let's see if I glossed over anything. Oh yeah, and then so here's what the book says about it, and they don't give any justification of it, and I haven't had time to sit down and figure out why. It says it also holds for elliptical orbits if you replace r with a, the length of your semi-major axis. Okay, so that's worth noting, that if you've got an elliptical orbit, you still can use it, but you just use a instead of r. Cool? All right, and I at some point need to sit down and see if I can figure out why. I just haven't had time to spend with it yet. Yeah, Patrick.
What's the squared here?
What's a square year? Is that what you said? It doesn't really have meaning. It's just, yeah, I mean, it's just a means for problem solving, really, more than anything. Yeah. About the only, I guess, sort of meaningful use of square units of time I've seen would be like acceleration, where you have meters per second squared. But in that case, we're talking about, meters per second. So, yeah, you're right. Square years has no meaning. Also, our units here would be seconds. Everything here is standard units. Seconds.
So it's kilograms and then meters for R and seconds for T.
Correct.
Okay.
Newtons per force. Am I missing something there? Meters for distance, did we say that?
Guys.
Cool. All right, any problems with that? Okay, so this expression of Kepler's third law does give us just some sort of general relationships. So, for example, it shows you that as your period increases, your radius increases, right? In other words, the farther you are away from the body you're orbiting, the longer it's going to take you to go around, which makes sense, right? And if you're good with ratios, you can use this, in a few instances to simplify things. So, for example, here's a simple example of a problem that you could do. So let's suppose that we knew, I don't know, the semi-major axis of Mercury and the period of Mercury, and we knew the period of Pluto and wanted to figure out how far away it was. Okay, so do I need to write that? Do you guys want me to write that down, or is that, do you guys see what I'm doing? Got it? Okay. So we know these two values. The ones in red, we know the green one is the one we're trying to find. Okay? So basically, do you guys agree both Pluto and Mercury are orbiting the sun, right? So this value is going to be the same for both Pluto and for Mercury, right? So that means that if I take t squared over r cubed for either planet, I ought to get a constant value, right? It happens to be this value, but who cares? It's constant. All right? And so what that means then is this. It means that I can take, what am I trying to find? We're trying to find, I guess I could have flipped it, right? Do you guys agree that I can flip it over and it still gives me a constant? A different constant, but a constant nonetheless. So that means that I can take r cubed for Mercury over period for Mercury squared and set that equal to r cubed for Pluto over t squared for Pluto, right? And then solve for the missing one, right? Make sense? And the other cool thing about this is because this is just ratios, the units don't matter. As long as these radii and these periods are in the same units, the units don't matter. Okay, so let's try it, see if it works. So let's see. So we should, according to this equation, here's what we get. So our radius for Mercury is 0.241. So 0.241 cubed over the period for Mercury is 5.79. Right? That ought to equal the radius for Pluto cubed over the period for Pluto, 248 squared. And solve it. All right. So when Kepler came up with his third law, this was his realization, was that this value is constant around any given body that you're orbiting. Okay. So let's see if it works, and hopefully we'll get 590. So let's see. Here we go. 0.241. What do we got? Cubed divided by 5.79 squared. And then I'm going to multiply by 248 squared. So that gives me the radius cubed. So now I want to raise that, take the cube root of it, right? So up to we'll do 1/3 power. And it gave me 2.95. What did I do? Do I? Oh. You're totally right. That's embarrassing. Sorry, F minus. So this one is our, sorry, columns got cut off. That's our A. Okay, so this one is our R, our A, and this one is our T. Sorry, guys. All right, so radius is 5.79 cubed over period squared, 0.241 squared. Does that look better?
Yeah.
Cool. Tell me when I'm being a bonehead. I guess you'd be doing that all the time, but 590 cubed. What am I doing? Jesus. r cubed over 248 squared. Wow. Sorry, guys. Apparently, I should not just make up examples on the spot. Right. Am I right now?
Yep.
Yeah.
Cool. 5.79 cubed divided by 0.241 squared gives me that, times 248 squared gives me that, and then take the cube root of it. 1 divided by 3, and you get 590. Hooray! Cool. Cool? Sorry about that. Sort of bumbling my way through that. Questions on it, you guys? All right, now notice this only worked, this little shortcut that I did here only worked because both Pluto and Mercury are orbiting the sun, right? If they're planets of different suns, then that would change, right? Because the big M would be different, so our constant of proportionality would be different. Cool? All right. I think, is that everything on that? Oh, kinetic energy. Yikes. Okay. I was thinking we were done.
If that was the case, could you just still with the proportion, but that would be R over M?
Oh. Yeah, because that's the only thing that changes there is the M. Yeah, so if you just, I think it'd be R times M, right? Oh, I gotcha. R cubed over M. Yes. Say it again. Right. Okay. Cool. Sorry, I was thinking we were done, and I was nervous. Like, how do we finish that quick? Okay. Cool. So, next issue. So going through a similar process, I guess I'm happy to go through this if you guys want, but it turns out that in the same way that I was able to relate the force of gravity to centripetal force, okay, you can use a similar process to rewrite the centripetal acceleration and find out that the kinetic energy is equal to this. Specifically this, I guess. Do you guys want me to run through how that works or no? It's just a bunch of algebra. Okay, so important things to notice though. Doesn't this equation look really similar to the equation for potential energy we learned? Right? It's the same as the equation for potential energy, but without the negative sign, and we've got this extra 2 on the bottom. All right? So, when something is in circular orbit, your kinetic energy is the same as your potential energy, but divided by 2, and it's got to be positive. Okay? That's huge. All right? Your kinetic energy is always half of your potential energy. That's what that is. Cool? So, following that logic, that means the E, our total energy, is literally half of the potential energy. Because look, if you take the kinetic energy, if you take this mess, and then add on the potential energy, right, this is basically 1/2 minus 1, right? Right? So you got half of something minus all of something, right? And it gives you negative a half of it, right? So this is, oh, we need an extra little bit of space. So this means that, so that Halley's Comet problem that I was doing before, I could have skipped some steps there if the orbit had been circular. But because it was elliptical, that was sort of where things got complicated. But notice, this is literally half of your potential energy, like down to the sign, right? Right, because it's still negative.
That's only for circular.
And it's only for circular orbit.
That's like extremely rare.
Yeah, but many bodies have orbits that are so close to circular that you can fudge it.
Really?
Yeah, like the Earth's orbit has an eccentricity of like 0.05 something or other. You know what I mean? It's almost 0. Cool?
We measure ourselves against other planets.
How do you mean? We're better at sports than other planets. Is that what you mean?
Like,
Sorry.
we know where we are, like, relative.
I think that joke was funnier than I got credit for. I'm sorry, one more time. I'll stop interrupting you.
How do we know where we are relative to other planets like that? know again.
Oh, I gotcha. I would have to review that. My astronomy is sketchy. It's been a while. I'd have to go back and look at it. I will say that I know at least a piece of that can be done using the Doppler effect by finding the frequency of the light that is emitted off of it. You can calculate the velocity of the body using the Doppler effect. I'm guessing that's a piece of it, but I don't think that's all of it. So I apologize. That's totally a question for Hernandez. All right. Good, you guys? All right. All right. So basically, this just kind of summarizes what we just... Oh, I guess I didn't point something out here. I guess also worth noting, this is the same as the opposite of the kinetic energy, right? Because...
Oh.
Man. Right? Kinetic energy was negative U over 2. Total energy is positive U over 2. So energy is just negative K, right? So if that helps you any. If you know either your kinetic energy or your potential energy, you can find your total energy. Or circular orbit. Cool? All right. All right, so that's what this first bullet up here says. For an ellipse, again, so it turns out that does this still work? I don't have that written there. For the energy of oh, I forgot about this. I'm sorry, guys. Bad when I sound surprised. So it turns out, apparently, why do I not remember this? Let me drop my notes. Hang on. All right, so I guess I shouldn't have stressed that, you guys. I was over here. I was stressing that it was only true for a circular orbit. So replacing R with A like we did before, it still works for elliptical orbits. So this calculation would have made our Halley's Comet calculations easier. So there you go. So this graph is meant to give you sort of a pictorial representation, right? So the idea here is the green line represents the total energy. All right. Notice that the kinetic energy is the same thing, just reflected over the x-axis, right? Same thing but positive. And the potential energy is just half of it. Hence, that's why it's lower down, right? So it's half as big. Okay. Cool. I feel like I'm missing something here. Right.
Wait, so it's like impossible for an object, no matter where it is in space, to have like zero energy.
Well, I mean, it's always going to have some potential energy relative to something, right?
Yeah.
You know, because you're,
That's more than mine, but anyway.
unless you're an infinite distance away, right? So yeah. Okay. Cool. Okay. Cool. Sorry, trying to think if I needed to say anything else there. All right, so one other quick thing that you should be conscious of is then, all right, so great. So what determines if the object is in circular orbit, elliptical orbit, or other? Okay? So it turns out that there is one specific velocity that will achieve circular orbit. And we actually referenced that over here. What is it? So it turns out that in order for something to be in perfectly circular orbit at a given radius, this is the required velocity. Okay, and that's, because we derived that by using the equation for centripetal force, which presumes that your object is in a circle, right? So that is worth making a page of. So recall from yesterday, we learned that the escape velocity of an object was this. right? Does that look familiar from yesterday? All right. So similarly, this is often called V circ. Oops, that is not how you spell circ.
That's exactly,
Say that again.
that's exactly what I wrote.
Okay.
Wait,
Go ahead, Alex and then Patrick.
so that's the velocity required for like perpendicular to the body?
Yes. Yes, because if you're in circular orbit, by definition, you're going to be
Yeah.
perpendicular to the radius is a better way to say that, but yes.
So like, if I was like, if I wanted to put an object in a perfectly circular orbit around the moon, I'd have to launch it perpendicular to like the moon.
Perpendicular
at
to
that
the moon's radius.
Well, yeah, at that velocity.
Correct.
Okay. And it has to stay at
Where r is the distance you are away from the center of, in this example, the moon.
Yeah. Gotcha.
Good? All right, and I'm not done with this. I'm going to show you guys something else, so bear with me here for a second. But yeah, Patrick. It's the radius of the orbit. So following with Alex's example, if this is the moon, here's the center of the moon, and then here's my satellite that I want to orbit it, then this would be my r. Um,
Well, any velocity would give you an elliptical orbit.
you.
Yeah.
If we want to throw it in a
This one is specific to circular because it relied on that centripetal force equation, and I'm about to show you how you get to elliptical. That's sort of where all this is going. Okay. Are we good or no? You okay, Kurt? Was that a frustrated throwing of the pencil, or was that just a? Okay. All right. Everybody okay? All right. So now the question becomes: all right. Well, what happens if we're here orbiting the moon, but we're moving faster than this velocity or slower than that velocity, right? Okay. So. So here's our object that we're orbiting. Here's our satellite. All right, so this blue path is going to represent, circular orbit. Very badly, though. I was trying to draw a circle and failed horribly. Let me put it farther away. That'll make this easier. All right, so here's my satellite. All right, so the blue represents if the velocity of the satellite equals v circ. V satellite. Cool? All right. So, what ends up happening if the object is going too fast is it gives you an elliptical orbit outside of this circle. So this red one that I'm about to draw is what happens if the velocity of the satellite is bigger than than v circ, the velocity required to go in a circular orbit. And it'll do this. Where this is one of your foci, and this is your other foci. Right? In other words, it's sort of going too fast for gravity to pull it in at that tight of a radius, and it takes more time to be pulled back in. Cool? And I should probably comment that's assuming that it's not going faster than the escape velocity, right? Because obviously if it's going faster than the escape velocity, then it'll escape and won't orbit at all. Follow? All right, so then what's the other possibility?
Inside the circle.
Yeah, exactly. So if the oops, I was trying to do that in a different color. So if the velocity of the satellite is less than the velocity required for a circular orbit, then gravity kind of takes hold of it quicker, and you get an orbit that looks like this, where here's your focal point, focus, whatever you want to call it, and here's your other one.
Celestial bodies typically stay in like the same orbit because there's really not like much energy being lost, other than through like gravity waves and stuff.
Yeah, more or less.
Okay.
Yeah, I mean, there's some, the moon is slowly spiraling closer to the Earth, but I mean, it's like millimeters per, century, or I don't know what the numbers are, but yeah. Cool, you guys? All right. I guess that's it. And does this drawing make some kind of intuitive sense?
Yeah.
Cool.
Whatever. Space, we have two working and they pull on each other.
Then that's when you've got to calculate the net force as a result of the two objects that are causing the gravitation. Or is that not what you're asking? Say it again. Keep cutting you off today.
I don't know. No, I just know. Thing. Like last year we did this crazy lab. We went online and we like played with masses and stuff. And we orbited one thing around it, and that was just kind of going crazy. And then like the middle thing was like supposed to be the sun, and then that moved a little bit too.
I gotcha. Yeah, I mean, the more objects you put into it, the more complicated the motion gets.
Oh, no,
more forces, and you get acceleration in more directions. Cool. All right. Wow, is that done? We talked about this. We talked about that. So what we just talked about answers this checkpoint. So take a second to read it. Make sure that you understand it. So let's see, in the figure here, a space shuttle is initially in a circular orbit of radius r around the Earth. At point P, the pilot briefly fires a forward-pointing thruster to decrease the shuttle's kinetic energy. Does that make sense? What does it mean when it says forward-pointing? In the direction it's going, right? So it's going to slow it down. Hello, is Mr. Striker? I do. I will do that as Mr. Yeah, okay. Yep. Yeah, we'll do. Yep, bye. Mickey, Mr. Take this one, so you to stop by on your way out today.
Really?
Yep. Doesn't have to be right now, just before you leave. Okay, so yeah, so the idea is the shuttle's moving forward thrusting thruster, worst sentence ever, is going to slow it down. What's that going to do to the orbit?
Let's work it.
Well, it's gonna slow the velocity down. So instead of following the black solid line, is it going to follow path 1 or 2? One, right? Because now it's going slower, right? And if it's sped up, then it would follow path 2. What's that going to do to the period? Decrease it, right? It's going slower, right? Oh, wait. Hold on. No. Hang on one second. Let's see. Is orbital period... sorry, I totally oversimplified that. Is orbital period T of the shuttle greater than, less than, or the same? Well, let's see. T squared equals K times R cubed, right? So our average radius decreased, so our average period is going to decrease. Cool? So even though it's going slower, the fact that it's got a shorter distance to go overcompensates for it. Cool? Cool. Yes?
Speed you just get to orbit. Like, is there like a minimum speed that like you'll get to the atmosphere and then you'll fall down if you're below that? You can't get to orbit.
Right. I see what you're saying. I know the answer for circular orbit. You would have to. So let's do the moon for a minute, just because it doesn't have an atmosphere to deal with. Okay. So what you would need to ensure is that at whatever orbit you're at. So suppose I'm trying to orbit the moon, right? Right, and suppose I'm here, right? So, if you're going at a velocity that equals the circular velocity, everything's good, right? If you're going faster than that, everything is good.
Like the moving planet.
Well, that's escape velocity that you're talking about.
Or it doesn't escape velocity put you at like outside of one.
Yeah.
If you're gonna do the elliptical one, you're less.
What are the minimum speed required to achieve?
Right, that was how I interpreted your question at first, but then I thought you steered me in the other direction. So that's where I'm going. So give me 1 second. So there's one specific velocity that will achieve circular orbit. Good with that? All right, if you go faster than that, you're good, because then you're in a bigger elliptical orbit. And you're wondering, what's the smallest orbit I can have so that I don't crash into the Earth, or the moon, right? So what you'd have to do is, I think you'd have to do it using conservation of energy, and figure out what your gravitational potential energy is at the surface of the moon, and ensure that your total energy at this point is enough that, how would you have to do it? Yeah, such that your gravitational potential energy never got to this point. You know what I mean? So you'd have to do it using conservation of energy. That's an interesting question, and I'll monkey with that. It seems like there should be an easy answer for it, but I don't know what it is offhand. I've never seen that before.
If you like get really close to the surface, like you could be like poking
Shh, guys, quiet. Well, but it's possible your other if your other focus could be still inside the moon, depending on the shape of your orbit. I gotcha. Yeah, I guess you could do that. Yeah, I like that idea too. Right, yeah, so you're saying, assume that it just barely hits over here. Now you know the shape of your orbit, you know the length of your semi-major axis. What else would you have to know? You'd have to know the eccentricity of the orbit too, though.
Yeah, that's what I was saying.
Right.
The smallest velocity would just be a circular orbit about
No, because you can stay in orbit and be going slower than that circular velocity. That's what.
yeah, but I mean like you're traveling in a circle like right in the radius of the moon. So
Traveling in a circle.
basically like a meter above the surface.
Oh, I see what you're saying.
The smallest velocity.
Oh, right. That might work. Right. You might be right. Let me look. I think Sam might be on something. All right. So anyway, so we have a couple questions to resolve. The first chunk of 13 is due tomorrow. Just out of curiosity, who knows for 100% sure they're not going to be your friend?
Mr. Ecker, can we do the homework Friday? Yes. Test tomorrow because people look online for the homework today. That's that.
Do you guys prefer that?
We can Skype them in.
Who's not going to be here tomorrow? Would you guys rather look at tests tomorrow? But then you guys.
Yeah.
All right. Tentatively, homework is due tomorrow. We'll see how it goes. Sorry?
Actually, I think it would be the opposite. You would take up an opposite. So like if you're just